All right, good morning, everybody. Are you guys able to hear me?
Yeah, I can hear you.
All right. That's good. Wade can hear me, so at least you and I can have a good meeting, right?
There you go.
Okay, I am recording the meeting in case, people aren't able to join right now and they can watch it later. Or better yet, because Wade's going to drop some knowledge and we'll all want to watch it later, right?
Hopefully.
Yeah. I just have a couple of things, and then Wade is going to basically talk about kind of some HVAC 101 stuff that I feel like all auditors should really understand. I think it's going to be really good for technicians and QCIs as well. So that's kind of the plan for the meeting today. I'm on somebody else's computer this morning, so I might be even more, I have more struggles than usual. So yeah, I just got a few things I'm going to go over. I got a couple quick slides to talk about these things. And then just the last one I don't have a slide for is that our next technical meeting will be on November 5th. And then, as I mentioned, the main topic, we'll turn everything over to Wade for that. So I just wanted to make everybody aware that we realized about a month ago that there was no link to this BPI 1200 quick reference card that we use quite a lot in the program. So we just added a link to that on our resources page. So if you've been looking for that, if you don't have a copy of it, you can just go to our resources page down in the NEAT audit section. It's right down at the very bottom of the list right now. It just says BPI 1200 quick reference card. That does not include the entire 1200 standard, but it covers most everything that you'll deal with on a day-to-day basis. So make sure you've got that and you're aware of where it's at. So any questions on that? All right. The other thing I wanted to tell everybody about was just DOE put out a program notice. It's number 19-5, and it's additional guidance on incidental repairs. And based on that guidance, we had to make a couple little tweaks to our guidelines, which they'll just get published the next time we publish a updated version of the guidelines. But the main takeaway from it was that DOE is getting very specific that what I wrote here on the screen, that a justification for the cost of each IRM and why it's necessary for the effective performance or preservation on an ECM, that justification must be documented in the file with photos and a written explanation. So that's their language, and the intent was there, but I actually went in and added that language specifically into the IRM sections of the guidelines that spoke, wherever the guidelines talked about IRMs. So if you are doing any incidental repairs, make sure that you are writing down a written justification. If you have any questions on how to do that, that's already in the guidelines. It has examples in section B9 on how to do that. And the other thing is make sure that you have photos to back up what your written explanation is. And then the other thing they outline in there, which this has been in our well, it hasn't specifically been in our guidelines, but I have told many auditors that this is allowable, but DOE, their language specifically prohibits it in this program notice. So please be aware that window replacement can no longer be done as part of air sealing. So I know I've told a lot of auditors that it's okay that you could put the window into your air sealing budget or into your air sealing strategy if you have room, but the DOE language in this guidance says that is not allowed. So we've clarified that as well in the guidelines. Any questions on that? All right. Refrigerator replacement. We've talked about this a little bit over the last couple of months. And we had a great question that came from the field, and Brad's been doing his homework and trying to find answers to the questions that he got, and he was able to get answers from both Rocky Mountain Power and from DOE. So basically, DOE, as it says right here in the middle, DOE does not have any limitations on side-by-side refrigerators. They also don't have any replacement on ice and water through the door. Brad was able to confirm last week that the program notice from 18 years ago that had that language in it has been superseded, and that is no longer an issue for DOE. So, and then the RMP, we had a question with RMP about that RMP used to limit that our refrigerator rebates they wouldn't do a rebate on a refrigerator that had consumption higher than 500 kilowatt hours per year. And that is no longer the case as well. So there's no more limitations on, no more RMP limitations. There's no limitations on side-by-sides or ice and water through the door. So this language will also change when the guidelines are updated. But you guys can begin right now following this guidance. So the goal with refrigerators is that we evaluate the primary fridge in every home. That should be the one inside the envelope, typically in the kitchen. And we're only evaluating one, or you can evaluate a couple of them, I guess, but you can only replace that primary refrigerator. We are replacing like for like, and they must be Energy Star rated. That's really, you could stop right there, but basically there's no more limitations about ice and water through the door. There's no limitations on RMP's rebate about how much power it consumes. The goal is that if the refrigerator saves energy, you can replace it. Does anybody have any questions on that?
That's fantastic news.
Yeah,
Sounds great.
I hope it simplifies things a bit. So
Absolutely.
cool. All right.
Yeah, I had the chance, just to jump in real quick, I had a chance to have a conversation with Erica while I was out there in Arkansas last week and talk specifically about this. And at some point, they're looking to update some other guidance as well. They will provide more language on this, but straight out of her mouth to me was, it's not a problem, don't worry about it. So like I said, with the opportunity now to get the rebates as well from RMP, I mean, that $1,300 side-by-side is looking pretty, yes, we still need an SIR, Jesse. If it saves energy, replace it.
Yep.
But
Exactly.
yeah, if the chance to, get 50% back on that thing as well, that's a pretty attractive option now.
Yeah. All right. The next thing, Brad sent out an email to all of your program managers. Just wanted to make sure everybody was aware that he's put together an additional training opportunity for the Nest thermostats. And basically, he's authorized agencies to purchase Nest thermostats, the E version, the one that we're giving our clients, for all staff who would, in their normal course of work, be directly involved with the installation, maintenance, troubleshooting, or assisting a client with the device. Basically, if staff have these in their homes, we feel that you guys will be better equipped to help clients understand how to use them, and that you'll be it'll be a good learning opportunity for you. So we felt like the cost of the equipment was worth allowing that. He's given very specific guidance to your coordinators on how to purchase those and stuff like that. But hopefully some of you have got them. If not, talk with your coordinator if you feel like you fall into this category. So any questions on that? Does anybody out there have them in their home already, because based on this training opportunity? All right. Well, bug your coordinators and get them in your homes, because I think it'll be a good opportunity. And then the other thing I wanted to make sure everybody was aware, I talked to a few people and some know, some don't. Your DG1000s, they just put out an update. I think they actually updated it a couple of months ago, but make sure you have the latest version of software on your DG1000. And if you do, and you're using an Apple product to run it, then it will, when you open the app on your Apple product, make sure that the tech type stuff is up to date on your Apple product. It will automatically launch to your Bluetooth instead of your Wi-Fi. So it will now communicate with the DG1000 via Bluetooth. So your Wi-Fi can stay connected to the internet, and you can get your location and your outside temperature and everything else you need. So it's a really nice update. Just anyway, be aware of it. It's not available for the Android devices yet, but they're working on it. So hopefully soon. But I noticed that when I launched it on my iPad, it automatically turned on my Bluetooth, connected via Bluetooth, and allowed me to stay on the internet. So any questions on that one? All right. Well, that's all I had. Wade, I'm going to turn it over to you, man.
Turn it over to me and I'll go.
Maybe I'll turn it over to you. There you go.
Okay, can everybody see my screen that says Furnace 101 Learning Objectives with my cursor spinning around in the middle?
Yes.
Okay, thank you. All right, so this is 101, like Matt mentioned. Any of you furnace guys that are out there, this is going to be basic stuff for you. You should already know. For auditors, QCIs, and other people, there should be some good information in here. Our learning objectives, you're going to have the ability to visually identify various furnace types. You're going to gain knowledge of universal furnace components. You're going to understand the basic furnace sequence of operation. And then I have some videos on some basic troubleshooting and service techniques. The videos are a little rough around the edges because trying to get video editing software on my state computer is a frickin' joke, so I had to do it all on my home computer and transfer it over. But I think it'll get the point across, and because it's all recorded, if you're out in the field and need to go to one of those videos to figure something out, it'll help you. Again, it's very basic troubleshooting. We're not going to get into any heavy-duty, in-depth stuff on that end of it. So let's go ahead and get it rolling. If the PowerPoint will work. There we go. So first thing we want to start with is quick visually, how can I tell what these furnaces are? I've got 3 furnaces up here, this one, and this one. All 3 of them fall into a different efficiency category. It's super easy to tell just by looking at the front of the furnace. So we'll start with this. Everyone notice this one's got a great big hole in the front door. It's called a draft diverter or a draft hood. Any furnace that has this on it falls into the 60% or what we classify as 60% efficient range. We'll talk about this draft diverter or draft hood here shortly. Also take note of the louvered front doors, okay? Anything less than 90%, so like this guy over here is an 80%, and notice the big hole in the door is gone, but we still have a louvered door. Anything less than 90% will have some kind of louvered door on it to allow combustion air to get into the burners. And then of course over here we have a 90%. The quickest way to tell is the flues. Anything that's 90% efficient or higher is going to have typically some kind of plastic flue because the flue temperatures are so low. Everything else is going to have some kind of metal flue. So that's one quick way, just by visually looking at a furnace, you can determine generally what efficiency range it falls into. If it's got some kind of draft hood, and sometimes you'll even see them up here on some older furnaces. It almost resembles what you see on a water heater. There'll be a draft hood up here. It's not quite as common as this guy here. If there's no draft hood but a louvered door, you're somewhere in the 80% efficiency range. No louvered doors, plastic flues, 90 percentile range.
Hey, Wade, I got a question on that.
Yeah, go ahead.
And maybe you plan to cover it, so I apologize.
No problem.
Which of those requires a worst case draft test?
So this one requires worst case draft testing. You'll see why here in a minute. This one does too. This one can backdraft. This one, if it's installed correctly, and we'll talk about the difference in how these can be installed. The way this one is installed, because it's a direct vent appliance with 2 pipes, there is no chance of backdrafting this into the envelope. But these 2 guys over here, they can backdraft, including this one. Okay, it takes a lot to get this guy to backdraft, but it can happen. So this one and this one should both be tested under worst case conditions. This one's a direct vent, don't need to worry about it.
So the one in the middle must be tested because of those combustion air louvers, right? Because if the CAS was really negative, it could actually draw air back out of the flue. Is that correct?
Absolutely. Yep. It can actually pull air back out. Now we'll get into it. I've got some more slides on it. We'll get into it. But there are safety devices built into these that will typically shut them down. But when these backdraft, they actually cause flame rollout. And they can actually cause all kinds of damage to the furnace and start a fire. But we'll get into that a little bit more as we go through this. So let's start with the 60 to 97% efficiency characteristics. So now this one over here, I pulled the front door off of it so you can see what's going on in there. Again, we've got the draft hood or draft diverter, which this allows air from the envelope or air from the room that it's in to go into the flue. This is a hole that is a direct connection to the flue. So this can backdraft flue gases right back out of this guy here. Also note the burners. Okay, see the big louvered compartment here? That's so that when this is running, combustion air can get into these burners, so we get an air-fuel mixture. Okay, so that's one of the things that you'll note, one of the visual characteristics of anything in the 60 to 97% efficiency range. And notice in this one, there is no inducer motor anywhere. That's another dead giveaway. Okay. That it's less than 80% efficient, no inducer motor. We'll talk about this a little more. It's kind of hard to see in this picture, but we've got this aluminum pipe running from the gas valve down to the burners. That's the standing pilot. Okay, that's part of the reason why this is only rated around 60% efficiency, because of what's lost due to the standing pilot. Okay. So here's that draft diverter or draft hood that we talked about. I took my inspection mirror, took the flue off, and I can stick that right down through. It's a direct connection right into the house or the envelope, if you will. Here's a picture looking up through it, and you can see here's each burner compartment. So all the flue gases come out of here into the draft hood, and hopefully the flue's working right, and they all go up and out. If the CAS is under extreme depressurization, or something's blocking this flue, or the flue's designed poorly, those flue gases, instead of going up and out that hole, will just spill out into the room, spill out right through this guy. And it's pretty easy to tell if they've been spilling. You'll start to see black buildup and stuff, rust and things, just like you do on the top of a water heater that's spilling. You'll see that kind of stuff around this. Okay, so that's one of the things that you can visually look for to help you determine what kind of furnace it is or what efficiency it falls into. Another thing is that these 60% efficient furnaces will typically always have this style of burner. This is called a ribbon style burner. Note it's a very long burner, big long ribbon. Okay, you can see those ribbon style burners here in that furnace. And again, this is a good view of that pipe that goes down to the standing pilot light. Now, if you do a combustion analysis on this type of furnace, you'll probably get a combustion efficiency reading that's over 70%. And I often get the phone calls, well, I'm on this 60% furnace, and the combustion analysis is 73%. How is that possible? Well, the reason this is rated at 60% efficiency is because of this standing pilot. You have this pilot that's always on, and it's losing heat or using gas, and the heat that it produces is not being used to heat the house whenever the furnace is not running. So the manufacturer has to take into account the gas used versus the heat energy delivered to the house. And when you add up the amount of heat energy lost because of just this little standing pilot, it causes the overall efficiency equation on this furnace to go down to around 60%. That's why they started getting rid of standing pilots. That helped improve the efficiency, because you don't have this big old pilot here just burning 24/7. Like some of them burn all summer long. It's all just wasted energy. I've seen some pilot lights that are gigantic. I mean, they look like big 10,000 BTU burners. So again, ribbon style burner and a pilot light. And remember, if you do a combustion analysis on these, it's likely that you'll get an efficiency reading over 60%, but don't panic. It's just remember how they rate them. They've got to include that standby loss for the pilot in their efficiency rating. All right, the other thing, we talked about inducer motors. Anything that does not have an inducer motor falls into that 60% category, or anything under 80% efficient does not have an inducer motor. Again, we've got the louvered door still, okay, because combustion air has got to get into the furnace to the burners through that louvered door. But now notice the big draft hood is gone. Okay, we still have a metal flue, so that's a giveaway as to what efficiency range it falls in. But now we have an inducer motor. And in this particular case, on anything less than 90% efficient with an inducer motor, this inducer is simply sucking air and fuel into the burners and then pulling it through the combustion chambers. But once those flue gases get to about this point on the flue, they still depend on natural draft to get up and out of the flue. This inducer on this type of furnace, which is less than 90% efficient, does not force the flue gases up and out of the flue. I've seen furnace techs with a lot of experience, they've been around for years, had the misconception that this inducer motor on this furnace actually pushes those flue gases out. It does not. This still depends on natural draft. And back to Matt's point, this can backdraft. If you get a CAS that it's negative enough that overcomes the effect of this inducer sucking air and fuel into these burners, it will backdraft right back through the combustion chambers and start spilling out of these burners. And there's little protection guys right here like this, if you can see it. That's called a rollout switch. There's another one right here. Should this start to backdraft, it causes the flames to roll out. Hopefully the rollout switches shut everything off before it burns up all the wiring or starts a fire. So that's why these types of furnaces still need to be tested under worst case. If you get a CAS that's negative 15, 20, you can backdraft these. I've seen it happen. And you'll know, you'll see all the burn marks from the rollout happening, that type of stuff. If it's locked out due to a tripped rollout switch, probably a good chance that it's backdrafted. Okay. Any questions so far at this point? Okay, very good. We'll move along. Okay. All right, here's another thing you can look for. Remember the old ribbon style burners? Anything that's 80% efficient and higher is typically going to have these new in-shop burners, and they look like little jet engines when they're running. Okay. You won't see this on the older, what's classified as 60% efficient or anything under 80%. Now, there were some very old first attempts at 80% efficient where they used a ribbon style burner with an inducer motor, but you won't run into too many of those out in the field. They did those for a year or two and then gave up on them, and everything 80% higher switched over to these in-shot style burners. Okay, so another dead giveaway of what kind of efficiency you're dealing with. Okay, and then of course here we have 90% efficient. Okay, and the giveaway here is the flues. If you've got plastic flues of some sort, then that means the flue temperatures are so low that it's super efficient. It's taking all the heat energy out of the gas, putting it in the house, thus causing lower flue temperatures. So we've got exhaust and intake, and they should both run to the outdoors. That's the proper way to do it. That's called direct vented. And it's got a sealed combustion chamber down here. There's no way that you can cause this thing to backdraft into the house. If it were to backdraft for some crazy reason, the flue gases are going to come down here through the inducer, through all the heat exchangers, sealed combustion chamber, and back out here. I have yet in my lifetime to see one of these things backdraft, okay? Because they're sealed combustion and because they're vented properly in what's called the direct vent configuration, 2 pipes to the outside. Now, here's a job performed by Weatherization where they got lazy and they only ran the exhaust pipe up and out and they left the intake wide open. Now note, there's not a sealed combustion chamber here like this guy. The sealed combustion chamber can actually be the front door going on it. And remember in the pictures before, the front doors on 90 plus have no louvers. That's because the combustion air comes through here. Now the manufacturer of this particular equipment will allow you to install it this way. It's no longer a direct vent appliance. Falls under a different set of rules for terminating the flues. Okay. This is absolutely not allowed in our program. We should always run 2 pipes, and if you can get one out, you should be able to get the other one out. But the problem with this now is it's become very unsafe because now this could backdraft and the products of combustion will spill right out of this guy into the house. The other problem is this is sucking air, a lot of it, just like a fan, and it can cause depressurization in the house. So now if we've got a water heater that's right over here next to it, this is going to contribute to backdrafting the water heater. Just a horrible way to do it. And then the door they put on this was a door that screwed on and sealed up, and so this thing was actually sucking its combustion air from all the holes that were left in the attic. You can see they didn't glue one of the joints properly. This is all condensation that has been dripping down, and a fine plenum install there. But again, the main point here is, yeah, the manufacturers will allow you to do this, assuming you have enough combustion air in the room. So there need to be combustion air from outside into the room. But in our program, this is not allowed. You need to run both of those pipes to the outside. The primary reason is for safety. When they're both ran to the outside like this unit is safe and it can't backdraft. Any questions about this so far? All right, keep going. So again, we talked about 90%, no louvered front doors, okay, because my combustion air is brought right in through a pipe to a sealed combustion chamber. So that's another dead giveaway. 2 plastic pipes, they should both run to the outside. The other thing is anything over 90% is going to have some kind of condensate drain that comes directly out of the furnace. So here I've just pulled the door off the furnace to verify. Yep, I can see I've got a condensate trap in here with some plumbing that runs over to a pump. Now don't get that confused with this drain up here. You can have a furnace that's not a 90% and still have a condensate drain coming off the coil. This is for the air conditioning side. If it's 90%, you're going to have a condensate drain coming directly from inside the furnace somewhere and then going out to some sort of drain. So another dead giveaway of what kind of efficiency you're dealing with. Okay. The inducer motors on 90% efficient furnaces do actually force the flue gases out or pressurize this flue. Remember I talked about on the 80% that the inducer motors, once the flue gases get to roughly this point, they rely on natural draft. on 90% efficient furnaces, this guy actually forces the flue gases out. So this pipe is under a positive pressure. That's why it's so critical to make sure that all the joints are sealed. The building code even says that you have to use a contrasting color primer with glue. It's because the inspectors want to be able to see, did they actually glue all the joints? Did they primer and glue them so that they'll be tight? Because remember the picture I showed you before with all the stuff leaking on the flue. So we need to make sure that these flues are sealed up good because they are under positive pressure. This guy not only is sucking air and fuel into the combustion chamber, but it's now forcing the flue gases out under a positive pressure. Okay? All right. So here are some differences that you'll note. So one of the key things I want to point out on this is notice over here, so this is a standard efficient or anything less than 90%. Notice where the burners are located on this. They're located down low, so the flue gases have to move up through the heat exchanger and then out the flue. All 90% furnaces, in order to help with heat extraction, to get more contact time with the air, the burners are up on the top. Now notice the flue gases have got to be pulled down through the heat exchangers by the inducer motor, and then they're blown out of the flue. So that's another key difference that you'll note. If you just open the door and you see the burners down low, flue up high, well, then it's less than 90%. Burners up high, okay, that's usually an indication that it's a 90% efficient furnace. And it'll have a primary and a secondary heat exchanger. Okay, now there are some exceptions to the burners up high rule. This particular furnace is what we call a downflow. That's another basic thing you need to know. Furnaces can blow air different ways. So the air in this furnace is sucked through the return, goes down through the furnace, and then is delivered into the house. Notice on the downflow, the burners are not on top anymore, they're down low. And the blower motor's back behind this door. So the blower's on top, that means the air is blowing down. But if I were to flip this furnace over, which I can because it's a multi-poise, the burners would be back up on top when it's in upflow condition. Okay? That's the other thing we want to talk about, upflow versus downflow. So this is a great example. This is a mobile home furnace right here in the middle. Typically, most of the furnaces you run into in mobile homes are downflow. So the air sucked in through the return. There's the blower. It blows the air down across the heat exchangers and out into the mobile home or the house, whatever the case may be. But again, that's the one instance where you'll find on a 90% that the burners are not up on top. Okay? But if I were to flip either one of these over and make it an upflow, now the burners are on top. Over here we have an upflow furnace. You can see the blower is down low, so air is sucked in through the return and delivered up. And again, because it's an 80%, I've got an inducer motor. The front door is going to have louvers on it, and my burners are down low, in-shot burners. The flue gases have got to go up through the combustion chamber into the inducer housing. Once they get to this point, natural draft takes over. We have to have a good flue that slopes upwards to get the flue gases out. Any questions or comments to this point? Is everybody still there? Can you hear me? It's awfully quiet.
I'm still here. I can hear you.
Okay, as long as someone's still there.
We can hear you.
All right, good deal. Okay, here's just a quick thing. This is a manufacturer's installation guide, and it just shows different configurations of furnaces. So this particular manufacturer, their upflow furnace, again, the air blower's in the bottom, air blows up. They use a U as the designator in their model number for upflow. Their upflow furnace can be placed in a horizontal left condition. So I can take this furnace, lay it on its left side. We call this horizontal left. Okay. They have a downflow configuration designated with a D for downflow. And if I need a furnace that will go horizontal right, then I use the downflow, flip it on its side, and we have horizontal right. They also make furnaces, a single furnace that can be put in any position, so upflow, downflow, left or right, okay? Just depends on the manufacturer, but this just gives you some information. If you just get out the manufacturer's specs, it's amazing the things you can find out. So different flows, upflow, downflow, horizontal left, horizontal right, okay? All right, so you're an auditor. You're out on a furnace, the tag on it is missing. You need to know what the BTU input is because you've got to put that into the audit and stuff, right? You have nothing on the furnace to tell you what it is. So here is a quick trick to help you with that. Count the number of burners and times it by 20,000. So in this case, I got 20, 40, 60, 80, 100, 120,000 BTUs. That will work for practically every in-shop burner furnace you run across. There are some oddball ones out there that are 23,000 BTUs per burner, but still, if you use the 20,000 number, it's going to get you really close. Now, this one over here is different. This one is 25,000 BTUs per burner. So if I got 4 burners in there, what's my total BTU input? 4 times 25,000 is 100,000, okay? And if I were to look at the tag on this one, that's what it would tell me. So your burners, if you don't know what the BTU input is, count the burners times by 20,000, and that will get you really close. Just remember, there are some oddball ones out there that will do 23,000 per burner, and some that will be 25,000 per burner. But if you use that little rule of thumb, it will get you close enough to know what it is. You all know you can also use the Preston's guide. If you can find the model and serial number, you can look that information up in a Preston's guide, and it will give you the BTU input. And then, of course, figuring the output is easy. Just know the efficiency and do the math, okay? All right. So universal operating components. It doesn't matter what kind of modern furnace it is. Every modern furnace nowadays has pretty much all of these components. We're going to have a vent. Some of them have a vent switch, some don't. That's something you'll see occasionally, but not often. And usually the vent switch, you'll find it down here on the inducer motor. It's nothing more than a high temperature switch or something to make sure that the vent isn't overheating, or in some cases on some mobile home furnaces, it's to ensure that this motor is actually spinning before it'll start. You're going to have a vent or an inducer motor on practically every modern, well, on every modern furnace, unless it's under 80% efficient. You're going to have some kind of pressure switch and pressure hose. You're going to have a flame sensor. You're typically going to have some safety devices like high limits, rollout switches. You're going to have burners. These are in-shop burners. If I didn't know what BTU input this furnace was, how could I figure it out? Count the burners and times by 20,000. 20, 40, 60, 80, 100,000 BTUs. You're going to have pretty much a transformer, circuit board. That board's going to have a low voltage fuse. You're going to have a blower motor and a wheel, a door safety switch. I can't tell you how many service calls I've been on over the years because somebody changed their filter and didn't get the door back on right and didn't fully engage the door safety switch. Okay, so if the furnace isn't running, that's one of the first things I check. Did they get the door back on right? Okay, you get that call, oh, I just changed my filter and now all of a sudden the furnace won't run. Bet you the door's not on right. And then a capacitor for the blower motor. So these are general basic components that you're going to find on just about every furnace you run into that's a modern furnace that's 80% efficient or higher. Any questions on any of these components? Oakley dokley. All right. This is what we call the universal basic sequence of operation. Every modern furnace you run across will have this basic sequence of operation. Okay. Your T-stat's going to call for heat by simply closing a switch. That's all a thermostat is a glorified light switch. It's either open or closed, and when it's closed, it's calling for something. In this case, for the rest of this presentation, we'll just be talking about heat since we're getting into the heating season. Anyway, the switch in the thermostat closes, tells the thermostat to start running. The inducer motor starts and runs a 15 to 45 second pre-purge cycle. A pressure switch of some sort is going to close, and power is then applied to an ignition device, typically a hot surface igniter, but there are some spark ignition systems out there. The circuit board then checks the condition of any safety devices. If the safety devices are operating properly, the gas valve will be energized. The air-fuel mixture is ignited, and flame sensing device proves flame. So the furnace has got to prove or discover that there's flames exist before it moves on. If flame is present, 30 to 60 seconds after ignition, the main blower motor starts. Main blower operates until a call for heat is satisfied. Burners are shut down when the call for heat is satisfied, and the main blower continues to operate for 60 to 120 seconds. So this is the basic sequence of operation. There are some other furnaces that have more to it than this, but again, this is Furnace 101, so we're going to start you with the basics. If you understand the sequence of operation, it makes troubleshooting a heck of a lot easier. If you know what's supposed to be happening, when it's supposed to be happening, then you can go through the process of methodically troubleshooting and figure out very quickly what your problems are. Okay? Any questions or comments about the basic sequence of operation before we go into some basic troubleshooting techniques? Alrighty then. First thing I do is always check for 110 to 120 volts at the unit, okay? This is the right way to do it. This non-contact voltage tester, that is not a good tool for troubleshooting furnace problems. I'm going to show you a video of why these tools suck. I can't tell you how many phone calls I've got. Hey, I got this furnace and it won't turn on. And my first question is, okay, what is your voltage? It's good. Well, what does good mean? Well, I've got power to it. Okay. How much power do you have to it? Well, I don't know. My non-contact voltmeter just says there's power to it. That won't work. You've got to know what exactly, how much power I have to it. Because you can have a problem with your neutral line, and this guy will still tell you that there's power there, but the furnace will not run, and this reading will be substantially different than 110 to 120 volts. So let's go ahead and take a look at that. Again, these videos are a little rough. I apologize, but I think they'll get the point across. So we'll go ahead and watch a video of why non-contact voltage testers are not good furnace troubleshooting tools. Okay, I'm going to show you guys why using a non-contact voltmeter to troubleshoot furnace problems is really a horrible idea. So here we have a meter. It's a multimeter, volt-ohm meter, and it will detect non-contact voltage. So basically all I have to do is push this button, and if there's voltage present, it'll let me know. Voltage present. Now we can go ahead and check that voltage and verify what it is. So I'm going to go ahead and hook my alligator clip to a dedicated neutral, and then I'm going to go ahead and put my probe on line. So right now I'm checking the main line voltage in. We should have somewhere around 120 volts. Okay, now I'm going to go over, I have the ability on this system to manipulate the neutral side. So with this switch I can simulate either a broken disconnected or a loose neutral wire somewhere in the circuit. It could be in a junction box, it could be in an electrical panel, it could be in a disconnect box at the furnace, but basically what we've done is we've eliminated the neutral. The problem with non-contact voltmeters is even though the circuit's not complete, there's no neutral, this still tells me there's voltage. And if I only use that for checking main power to the furnace, I'm operating under the assumption that I've got 120 volts to the furnace. The meter's telling me there's power there. Well, the reality of it is this. There's still power there. It's just that the neutral side is gone or disconnected, and it's not 120 volts. It's significantly less than 1 volt. So this furnace will never start and run. This is the primary reason why using non-contact voltage testers is just really a bad idea. Again, you just saw there is no 120 volts, but the non-contact volt meters tell me, oh yep, there's power to the furnace. So if I start troubleshooting based off of non-contact voltage, I'm not going to get anywhere. There is not power to this furnace, or at least not a complete, there is not a complete circuit for this furnace to operate. There is power to it, but not a complete circuit. So the first one was about checking for voltage and why non-contact voltmeters are not a good tool to use. You should always use a regular voltmeter, check for 120 volts at the unit. The next step I always do is I check for 24 volts. Now I'm going to show you how to check for 24 volts at the furnace circuit board. This simple test is another way to determine if you have correct mainline voltage to the furnace. If the mainline voltage is not correct, you will not get 24 volts at the circuit board. Step 1 is to hook your voltmeter to the R and C terminals on the circuit board. Practically every modern furnace you come across will have these terminals at the circuit board. The R terminal is always the transformer hot side, and the C terminal is the transformer common side. This simple test will not only give you an indication that the mainline voltage is correct, but it will let you know whether or not the transformer and low voltage fuse are good also. If you have correct mainline voltage to the unit, the door switch is properly engaged, the low voltage fuse is good, and the transformer is good, you will have 24 volts between the R and C terminals. And it is okay if your voltage reading between R and C is plus or minus 3 to 4 volts. Now let's take a look at the low voltage fuse. It is typically a 3 or 5 amp fuse, and it protects the low voltage circuitry from any short circuits or voltage spikes. If this fuse is bad or blown, you will not get 24 volts between the R and C terminals. The easiest way to check it is to pull it out and look at it. See the thin middle element in the middle? It should be intact and there should be no discoloration in there. If the fuse is bad or is blown, the element will be broken and there will usually be black discoloration in there also. You can check this fuse by hooking it to an ohm meter while you have it pulled out. If it is good, your meter will indicate a closed or complete circuit. If it is bad, your meter will indicate an open line, as shown by OL on the meter I'm using. As long as we are discussing low voltage, this is a good time to talk about the transformer. It is simply a device that converts 120 volts to 24 volts. It's also known as a step-down transformer. If the transformer is not receiving the correct voltage or is defective, you will not get 24 volts between the R and C terminals on the circuit board. Let's start by doing a simple check for correct voltage to the transformer. All you have to do is pull the line voltage wires off the transformer. Now, make certain the main power is turned off before you're doing this. Then connect your voltmeter leads to the wires that were connected to the transformer and turn the power to the unit back on. If you get a reading of 110 to 120 volts, plus or minus 5%, you know you have correct voltage to it. Once you're certain you have correct voltage to the transformer, you can reconnect the line voltage wires back to it. Now again, make sure the main power is turned off while you're doing this. And now you can pull the secondary or low voltage wires off the transformer. And this time hook your voltmeter leads directly to the terminals on the transformer. Now turn the power back on. And if the transformer is good, you will read 24 volts plus or minus 3 or 4 volts. If the transformer is defective, you will read 0 voltage on the low voltage terminals. Okay, now we're going to watch a quick video demonstrating the process for checking power to the primary side of the transformer and power from the secondary side of the transformer.
Okay, I've got my leads pulled off of the high voltage side of the transformer. I've got my meter set for volts AC. We've plugged our meter leads into those 2 wires going to the transformer. And when we flip the power to the furnace on, we should see 120 volts. That means that we have power to the transformer. Okay, now I've connected my voltmeter to the secondary or low voltage side of the transformer. Just took the wires off. I currently have the power turned off to the furnace, so we shouldn't be reading any voltage. What you're seeing there is just millivolts, just residual stuff in the system. I'm going to go ahead and flip the power back on. If we have correct voltage to the transformer and the transformer is good, we should see 24 volts plus or minus 3 or 4 volts. So now we know we have a good transformer in this furnace.
I got a few more. Again, these are all just basic troubleshooting stuff. Hopefully when this is all done, when Matt puts these out on YouTube, you can use these videos. If you're out in the field and forget how to do these basic tests, you can go ahead and do them. Just always use caution, especially if you're new to working on furnaces. I say it over and over again in the videos. Make sure the power is turned off while you're in there reaching around playing with stuff. If you're not used to working on them, you can grab the wrong thing and get yourself into trouble and real quick. Okay, next thing we're going to do is we've determined we have correct line voltage to the furnace. We've determined we have 24 volts. I'm going to show you a quick way to tell if you've got a bad thermostat or bad wiring between the thermostat and the furnace. Real simple measurement, takes just a second to do.
Okay, the next thing I'm going to show you is a quick and easy way to tell whether you've got a bad thermostat or bad wiring between the thermostat and the furnace. So right now I've got my alligator clips hooked on the W terminal, which is universally the heating terminal. When there's a call for heat, that terminal is energized. So power goes from R through the thermostat and back to the W terminal to tell the furnace, hey, I need heat. Okay. Right now the furnace is off. So come up here to the thermostat. You can see it's off. There is no call for heat. So right now we have basically no voltage. We're showing 345 millivolts, which is significantly less than 1 volt, and that's just feedback through the circuit board. That's common. But if we turn the thermostat on into heating, I've got it cranked up to 90, all of a sudden we're going to see we've got 24 volts or something very close to it. And again, that's testing between W and common. Now, if I go ahead and go up and turn the thermostat off, all of a sudden we no longer have 24 volts. We're reading millivolts, just feedback voltage through the circuit board. So that is a quick and easy way that you'll know right off the bat. If you've turned the thermostat up and the furnace isn't running, take a simple reading between W and C. If there's not 24 volts there, you either have a bad thermostat or a bad thermostat wire.
So I've got a few more of these videos. I'm just going to keep going. I know we're going to go over time a little bit, but again, Matt will have this recorded, so if you need to jump off, you can always watch it later. I'm just going to go through all the stuff that was in the basic sequence of operations. So the next thing we'd want to look for is, do we have an inducer motor that's running? And here's a quick way to check power to the inducer motor.
The next component in the basic sequence of operation is the inducer motor. If it is not getting the correct voltage or is defective, the furnace will not operate properly. Let's start by checking for correct voltage to the inducer motor. In order to do this, all you have to do is unhook the wires running to the inducer motor. In most cases, there will be a Molex plug you pull apart and check for correct line voltage at the plug. Always make certain the main power is off before disconnecting and reconnecting these wires. Now connect your voltmeter leads to the wires running back to the circuit board and turn the main power back on. Note, the thermostat must be calling for heat in order for this test to work. You should get a reading of 110 to 120 volts plus or minus 5%. If you don't get a correct voltage reading, you either have a bad circuit board, a mainline voltage problem, or defective wiring between the circuit board and the inducer motor. If you are getting correct voltage to the inducer motor and it is not running, then the motor itself is probably bad. There are a lot of things that can cause an inducer motor not to operate. One basic thing you can easily check for is the condition of the motor windings, which we will do in the next video. But right now, let's take a minute and watch a quick video on how to check for mainline power to the inducer motor.
Okay, I've disconnected or unhooked the Molex plug that goes from the circuit board to the inducer motor. I've hooked my meter leads into the Molex plug to the wires that go back to the circuit board. Currently the power is off, so I'm showing no voltage, or 1.9 millivolts, which is basically no voltage. I'm going to flip the power onto the unit, and if everything's working right, we should see 120 volts to the inducer motor. And there we go. So now we know we've got power to the inducer motor. So if the inducer motor was not operating, then we know there's a problem in the motor. Okay, so once we figured out that we do indeed have correct voltage to the motor, if the motor were not running, there's another simple check we can do to check the motor out and see if there's a problem with the motor. So we'll go ahead and show you guys that one.
In order to check the condition of the electrical windings in the inducer motor, first make certain the main power is off and use an ohm meter to ohm the motor windings. To do this, just set your meter to the correct ohm settings and connect the leads to the wires leading to the inducer motor. If the motor windings are intact, you will get a resistance reading of some sort. If you get an open line, or OL as indicated by this meter, the motor windings are broken or shorted and the motor should be replaced.
Okay, the next part in the sequence is the pressure switch. There's a super easy way to check pressure switches, so I'm going to go ahead and show you that. Before I run that video, any questions so far? All right, we'll just go ahead and continue on then.
The pressure switch is a safety device that is basically just a glorified light switch, which is always in the open position, or what we call normally open. When it senses the correct pressure created by the inducer motor, either a positive pressure or a negative pressure depending on the unit, it closes, telling the circuit board that the system is okay to proceed to the next sequence of operation. This particular pressure switch needs to see a minimum of 2.25 inches of water column of pressure before it will close. Pressure switches are relatively easy to troubleshoot. All you have to do is remove the low voltage wires leading to the switch, make certain that the power is off before you're doing this, and then connect the leads of an ohm meter to the terminals on the switch. You should get an initial reading indicating an open line or an open circuit. If you get a reading of any kind of resistance or continuity, the switch is stuck closed, and the circuit board will prevent the unit from firing due to this condition. The circuit board checks at initial startup to make certain the pressure switch is in the open position. This is to ensure that some idiot didn't simply run a bypass on the pressure switch to trick the system into running. Remember, this is a safety device. Safety devices should not be bypassed. They are there for a reason. They are there to protect people from possible life-threatening situations. Okay, once your ohm meter is hooked up to the switch and you have verified that it is in the normally open position, turn the main power back onto the unit. And if the switch is seeing the correct pressure, it will close. And you should now get a reading showing continuity or the circuit closing. The number you get should remain constant. If your meter indicates an open circuit or it is erratically jumping around, you either have a blocked or restricted exhaust or intake, a problem with the inducer motor, plugged or cracked pressure tubing, or a bad pressure switch. Now we'll watch a quick video of the process actually taking place. Well, you get the point, I hope. I'm not a very good video producer, especially with the limitations I had on me to do this. Anyway, any questions about that? All right, we'll keep moving along here and get you guys out of here. The next basic check is checking a hot surface igniter. It's real easy to check. Practically anyone can do it. So I'll walk you through how to do that.
The hot surface igniter is simply a heating element that when power is applied to it, it starts to heat up and glow. Once it reaches a temperature of 1200 degrees, it can ignite natural gas. Modern igniters are either silicon carbide or silicon nitride. The industry has started using more silicon nitride igniters as they tend to be more durable and can reach the correct temperature using less power. If you are working on a furnace and find that the hot surface igniter is not heating up, then there are only two possible problems. The first one is no power to the igniter, and the second one is the igniter itself is bad. I always start by checking for correct power to the igniter. This can easily be done by unhooking the Molex plug with the wires leading to the igniter and connecting a voltmeter to the wires going back to the circuit board. Now again, make certain the main power is off while you're doing this. Once your meter is connected to the wires, simply turn the main power back to the unit on. Within 30 seconds or so, you should get a reading of 110 to 120 volts. Now, some silicon nitride igniters only require 30 to 40 volts to work properly. So you want to make sure that you're familiar with the equipment you work with and the type of igniter it uses. If you get no power or a power reading significantly out of range, you have either a main power problem, a bad circuit board, or bad wiring between the circuit board and the igniter. If you are getting power to the igniter, but it is not heating up, then the igniter is bad. And you can easily check that by setting your meter to check for ohms and ohming the igniter. You should get a reading of somewhere around 10 to 100 ohms. If you get a reading showing open line or open circuit, the igniter is bad and should be replaced. If you get a reading well over 100 ohms, the igniter may still work, but that is an indication that it is starting to go bad. Also, I have seen on very few rare occasions in my 40 plus years of doing this, an igniter that had correct power, ohmed out okay, and was glowing red, but the gas wouldn't ignite. In order to figure this one out, I had to use an infrared thermometer to check the surface temperature of the igniter while it was glowing. And what I found was, for whatever reason, they were not getting hot enough. If igniters don't reach 1200 degrees, natural gas won't ignite. And for propane, the igniter must get to at least 900 degrees.
All right, any questions on hot surface igniters and how to check them? Okay, we'll move on then. Next in the process is a gas valve. Their basic gas valves are very simple to check. Bear in mind, this is 101 diagnostic. Modulating and multi-stage gas valves are a little bit different, but if you're going to learn to do service, you got to start with the basics. Okay, next thing I want to check is to see if we have 24 volts going to the gas valve. You see our gas valve has 2 wires to it. So all I have to do is unplug those wires and then go ahead and hook my meter
directly to those wires. Okay, I've hooked my meter probes to those two wires. I'm set for volts AC. We're going to go ahead and flip the unit in and call for heat. Okay, you can hear the inducer motor running. What we're looking for here is 24 volts. Now right now we're reading millivolts, which means basically no voltage. It's just small feedback voltage through the system. Okay, after 15 to 30 seconds of inducer runtime, we should get power to the gas valve. We're looking for 24 volts, plus or minus 3 or 4 volts. You can see here we've got 25.9 volts. So we know we're getting power to the gas valve. So if the gas valve were not energizing like it should, then the next step would be to check the condition of the gas valve itself. All I have to do to check the condition of this gas valve is move my meter probes up to the two terminals on the gas valves where the wires used to be. I set my meter to the ohm scale, and I'm looking for some sort of ohm reading. So generally, anywhere from 10 to 20 ohms is what you'll see. Could be more, could be a little less, just depends. But as long as you're getting a reading, you know that the windings in the gas valve are okay. If you get an open line, that's an indication that the gas valve is bad and should be replaced. All right. Next is checking for flame proving signal. So again, I've got a little video to take you through that. Real easy check. Okay, checking for flame rectification, or what we call flame sensing current, is another real easy check. If you're lucky, the furnace you're working on will have this convenient port that you can check flame current right there. But that's not always the case, so we're going to go ahead and do it the old school way. Okay, to check for flame sensing the old way, you need a meter that you can set to microamps DC. And then we go ahead, the flame sensor's right here, it has one wire connected to it. We unhook that. Okay, so I've unhooked my flame sensing rod from the flame sensing wire that goes to the circuit board. I put my meter in series, so I hooked one lead to the wire, and the other lead, the black one back there, is hooked directly to the flame sensor. I set my meter for microamps DC, and now I'm just going to go ahead and flip the furnace on, call for heat, and we're looking for anywhere from 2 to 4 microamps is a good strong flame signal. Okay, my burner's just fired. Getting a good strong flame signal. Running about 2.5, 2.6 microamps. Typically anything over 1 is good. Get up into 4 and 5, that's really good. If that signal is weak, so 1 or lower, I try cleaning the flame sensor first. If after cleaning it, the signal is still weak, then I'd go ahead and replace the flame sensor. Again, we've just wired the flame sensor in series with our meter, and we're set for microamps DC. Super quick and easy check to make sure we got good flame signal. Alright, we're getting close to the end. So the last part of the sequence is the main blower. I'm going to show you how to check for power to it, and then a simple test for ohming out the windings of a blower motor and checking a blower motor start capacitor. So here we go. Okay, so I've unhooked the wires going to the main blower motor from the circuit board, in particular the heat and common wires, and that's where I've hooked my meter to. Right now the power is off, so we're just seeing some slight millivoltage. It's just residual voltage. I'm going to go ahead and flip the power on, and the furnace is calling for heat. And what we're looking for now is to see if we're going to get 120 volts from the circuit board to the fan. Now the inducer's got to run, the igniter's got to start, the gas valve's got to fire. So this can take about 60 seconds before you're going to get power to the fan. Okay, inducer motor started up. Again, what we're reading here is just millivolts. It's just feedback through the system. You can't see it on film, but the igniter has started to glow. So it shouldn't be too much longer here, and if everything's working correctly, we'll see 120 volts at the circuit board, which if the fan wires were plugged into it, that means we'd get 120 volts to the fan. Okay, burner's just fired. So again, we got about another 20 to 30 seconds before the blower should start. And there we go. Showing us we have power from the circuit board to the blower motor. Now if I just let this sit here and run, eventually everything's going to overheat and shut down because I've got the blower motor wires disconnected. But now I know that power is getting, at least from the circuit board, to the wiring to the blower motor. Okay, so that's a real quick and easy way to ensure you're getting power to your blower motor. And then what we're going to do next is if you have power but the blower motor is not starting, then there's a couple of checks, simple checks you can make to ensure that the motor is good and the capacitor is good. And this is the last video, so when this is done, we should be over. So here we go. Okay, if you've made the determination that you have correct power to the blower motor, but it's still not turning on, then there's most likely a problem with the blower motor itself or the start capacitor for the motor. All of those are easy to check. All we have to do is find the speed leads. You can see in this particular case on the schematic, we have a black lead, a blue lead, a red lead, and a yellow lead, and then white is common. All I do is pull those speed leads off and I check each one to common. In this case I'll start with black, then I'll move to blue, then I'll move to red, and then I'll move to yellow. You should get some kind of ohm reading between each one of those speed leads in common. If you get an open line, then that motor has bad windings and should be replaced. If all of the speed leads check out and the motor's still not starting, then you probably have a bad start capacitor. And that's really easy to check also. So here we have a picture of the start capacitor. We're going to go ahead and pull it out. You need to be very careful with these as they're a device that stores energy. So the power can be off, and if you pull a capacitor and touch the two terminals, you can still get a shock, a very powerful shock. So whenever I pull them, I discharge them. You can do that with a screwdriver or a nut driver, as you see here in this picture. I just place something metal across both the terminals to discharge it. I set my meter to microfarads or MFD, and I measure the capacitor. Note the capacitor is marked how many microfarads it should be. In this case, this one is 10. You should be no more than 10% difference than what the capacitor is rated. If your reading is greater than 10% difference, then you need to replace the capacitor. That means it's either bad or going bad. Alright, that's all I've got. Sorry for the kind of crappy video, but it gets the point across, and hopefully you'll find it useful if you're out in the field and need to do one of these tests and can't remember how to do it. We'll have a video resource there, and in the future I hope to make more of these with better video editing software, and hopefully they'll be a little bit better. So there you go. Any questions, comments, or concerns?
Oh, thank you.
You're welcome.
Yeah, thanks, Wade. This was great. I feel like this is some good stuff for the field guys.
Yeah, hopefully. Again, this is basic 101 service stuff. If you guys found this valuable, we can do some more advanced service stuff like this. Just trying to keep these videos, you know, less than 3 minutes, 2 to 3 minutes on the videos. So if you need them in the field, you can use them. We can do some more advanced stuff, assuming I can get some video editing software on my work computer. We'll see about that. Anyway, you just need to let us know. If this works for you, great. We'll do some more of these. If not, then we won't.
Awesome. All right, let's go ahead and end the meeting. Thank you guys for attending, and have a great
Thanks,
day.
everybody.